That's so weird. New noises. I hate that. Seriously dislike that. Zoom. What are you doing to me? Driving me bonkers. That's so annoying. Morning, guys. Like that's not the sound that I want to hear at 9:30 on a Monday morning. I don't want to hear all these like beep boops. Save those beep boops for some other time. I'm gonna have to figure out how to not have sound. Where's the sound? Oh well, I'll figure it out later. How's your weekend, guys? How's Monday going? So far so good. Just wait a few moments here to let everyone just make sure they're in. Have had a few questions about the assessment this week, so we'll kind of briefly chat about the assessment, do a little kind of recap of some of the material I wanted you to take a peek at on Friday. And yeah, we should be in pretty good shape to start into actually doing some mathy kinds of things. Like sets are getting us close, but it'd be nice to start doing like some addition and subtraction and all that good stuff. So that's coming up pretty soon. Busy. It was a busy weekend. Oh no. Busy like work busy or busy like assignments and quizzes and things. Was it school busy or work busy? So same with Chloe. You had just busy in general. Yeah. I actually got everything I needed to get done pretty much on Friday, which was nice. So I was able to get up to Kelowna yesterday just for like a little visit. So that was good. My sister recently moved into her new house here in Benedictine too, so I was able to see her new house over the weekend, which is great. She's living by herself up on over by Play Estate Winery, like if you guys know that area. So she's like up over there by herself. So wanted to see me. So I did that on Saturday evening. Yeah, that was a nice little yeah, I mean, it was a long Friday. I had meetings from 4 o'clock till 9 o'clock on Friday. It was a very long Friday. But the nice thing about online meetings is you can kind of like get your work done while you're listening to those meetings. So I like not having to be there face to face sometimes. It allows you to be doubly productive, essentially. So yeah, I got most of this stuff done. As you can see, a lot of your assessment stuff that was posted up on Friday. And we should probably quickly chat about that kind of stuff too, because I've had a few emails over the weekend about the quiz and about the lesson plan portion of this first assessment. So, oh my God, can I turn that? Oh my God, I need to be able to turn that sound up. It's going to drive me bonkers. Okay, just don't come in late or I'll have to murder a small child. Okay, so there are two parts of the first assessment. So I want you to create a lesson plan, as we talked about, so that you have essentially a marked lesson plan given back to you before the draft is due for the unit plan. So this is just one lesson plan. You don't need to do more than one. You can do more than one if you want to, but I'm really only going to mark the first one. And the instructions, template, rubric, and the Dropbox are all here at the bottom. So inside this first Word document has the instructions. And so maybe let's just take a moment to just recap some of the instructions here. Let's see, let's open that up. Should have made these into PDF documents so they're easier to open. All right, so let's go ahead and share that Word. Okay. Dear Zoom work. XOXO Brian. Okay. Okay, so you guys should be able to hopefully see the general instructions here. If not, let me know. And so the idea here is to go into one of these grade levels. You can pick any grade level you'd like and any topic, single topic from that grade level that you like. So for example, maybe you're going to do number concepts to 100 for grade 2. You just need to pick one of these. I do not care if many of you choose the same thing. So there's no worry there. So pick whatever singular topic from one grade level that you'd like. And then the idea is to go to the curriculum, take a look at this particular bullet point from the curriculum, and try to find something that you can connect to set theory. And it could be any of the topics that we've seen from sets so far. So maybe you want to work with number concepts to 100, and maybe it makes sense to use Venn diagrams to talk about cardinality or to talk about subsets or something like this. So maybe that's a nice connection. Maybe when we get into, I don't know, grade 6 and we're looking at something like factors and multiples, Venn diagrams are really great to talk about union and intersections for factors and multiples, right? So to help students really start thinking about the difference between these two things and thinking about things like common multiples and common factors. So those are great ways to tie in set theory there. Right, so the idea is to grab something, right, like especially like grade 7, working with decimals, fractions, ratios, and percents, and using Venn diagrams to sort these kinds of things. Super helpful to see that in a more concrete kind of way. So pick one of these, get your creative cap on this week, and try to figure out a way that you can connect that to something that we've seen. So you don't need to connect to all of these things, but you should connect to maybe one or two of these things. If you can, in a way that makes sense for that grade level. So for example, if I'm choosing something from grade 2 and I want them to think about, I don't know, the Cartesian product, which you guys would have seen on Friday, I'm not going to have them write out all of the Cartesian product things, but maybe we're going to play a game where we are making choices, right? And the idea is to, we'll talk about this today, the idea is to make all of the possible combinations of choices. This is what the Cartesian product essentially is. So it's like looking at a menu and being like, how do I, or like going into Starbucks, for example, I think, is that the example I gave you, I think in the video? I can't remember. This is kind of my common one. You go into Starbucks and you have the choice of tall, grande, or venti, right? And then, I don't know, maybe you want a hot chocolate or a pumpkin spice latte or something like that. So how many different possible choices do you have if you can choose 3 different sizes and you have 2 different drinks that you want to have? Well, it turns out that it's a multiplication kind of problem. There's 6 different choices, and then you can actually list all of those different choices. And that's the Cartesian, I guess, a concrete example of what the Cartesian product does for us. Right. So obviously I don't want them to like write out sets and write out these ordered pairs in grade 2. That doesn't really make any sense. By grade 7, it makes maybe a little bit more sense to be able to do that. In grade 2, maybe we're going to be looking at a financial literacy menu. And we're going to be like, okay, what are all the different ways I can order these these different Canadian bills, right? Or something like that. So you can certainly make connections, I think, in a clever and unique way. And like I said, try to do it in a way that makes sense for that particular grade level. Please let me know in the chat or on the microphone in the next minute or so if there's anything that you have a specific question on about the generalized instructions. Okay, so then, like I said here in the instructions, the idea is to convince me as the reader of this lesson plan that you know how to connect one of these ideas to set theory. So remember, this is an assessment about the set theory portion of our course. So you should have some connections to set theory with some examples, right? So you should have some examples with some solutions that I can look at and really understand that you have some knowledge in this particular area of mathematics. Okay, so that's really the goal. The goal is less about we'll look at the marking key. So the marking key is still heavily weighted on the lesson plan, but there is a significant portion of that marking key that is allocated to set theory as well. So let's take a look at the rubric as well. That's the unit plan. Okay, downloading and opening. And let's pop over into the rubric. So the rubric's going to look very similar to your lesson plan rubrics for the unit plan. So I didn't really change much in the overall rubric. The lesson is still going to be out of 40. So your ability to look at one of those bullet points, connect that concept to the some of the content and big ideas in the curriculum, like that's still important in this lesson plan, fitting it into the specific grade level that you're choosing. But we're also going to be trying to make that connection to set theory as well. So I've allocated 10 marks to those examples and solutions that you're going to be giving for this particular lesson plan. So this part of your assessment will be out of 50, okay? So still think about the sequencing, think about if you need BLMs, how are those gonna work? What are they going to look like? And I know a few of you have emailed me some samples and I said, don't forget to actually have some worked examples that connect to sets. So that's kind of what I need to see, right? So you can talk about sets as part of your lesson plan, but you should also have some examples. What are the examples that you're going to use for, your hook or for your full activity? Are you using Venn diagrams in some kind of way? Is it going to be helpful for you as a teacher in the future to have that Venn diagram on a piece of paper like this? These are some of the examples we can use in this lesson. So attach those examples and solutions as an appendix. Or if you're going to be using something like a Blackline Master, you can create your blank Blackline Master and then fill in the solutions to your Blackline Master as well. All Blackline Masters probably should have a solution key attached with them as well, if it's something that you would be using as an assessment. Is that starting to make things a little bit clearer on what to do, or do you have any further questions? On the end of chapter assessments of the very two full lesson plans from the topic you selected. Oh yes, my apologies. That should be just one. Yeah, what I probably did by accident was copy and pasted that Dropbox. Yes. So let me edit that right now. I probably could just copy and pasted that from the unit plan and forgot to change the 1 to 2. Yeah, so it should just be 1. So please upload, let's go 1. If I can spell this morning, there we go. So 1. Nope. Moodle is not allowing me to spell properly. There we go. Please upload 1. Flash ELMs and list online resources. Yeah, so you don't need a reference page here, as I said. As long as you have, if you use anything from the internet, just make sure you list that as part of your lesson plan. And like I said, important here, not only to attach the BLMs and solutions, but also some examples from the set theory ideas that you want to discuss in this lesson as well. So you should have some we call it worked examples. So examples that you're going to be giving to the class, and then teacher solutions to those examples as well. And yes, thanks for that catch, Vincent. That has now been updated to 1 lesson. I don't need you guys going crazy. You don't got to spend like, 100 years on this lesson plan. So only 1. 1 is fine. So that's the lesson plan. The lesson plan covers the set theory portion of this first chapter. The quiz only covers the logic portion of this first chapter. Okay, so the quiz is completely logic, and it's a little mixture. So I've kind of given you some specs here inside the description. So you have 7 questions in total, and you're going to have a mixture of essentially true false questions. So like looking at statements, trying to figure out whether or not they're true and false. So expect some true false kinds of questions. And then we have some long answer questions as well. So long answer, some examples of types of long answer questions might be, here's a statement, negate this statement, and then you'll just type in your answer, click submit, and I'll be marking that after the quiz is over. So that's an example. Finding things like the inverse, the converse, or the contrapositive statement is another example of a long answer style question. Okay, so you should expect a little mixture of, like I said, true, false, as well as these kind of typing in your answers, these typed in long answer style questions. So you aren't going to get your full marks immediately after this quiz is done. It might mark the true false portion of your quiz and give you that mark, but I'll be looking at these quizzes and marking them after Saturday. So I'll probably mark them on Sunday on the 7th. Okay, so that's the first, essentially the first assessment, a lesson plan, so that we can get a little bit of practice doing that. And then you got this little quiz. When we get through the second section, we'll probably just end up doing a little quiz, I think, for the second section, because you guys are probably going to have to spend a little bit of time getting the unit plan stuff going. So I'm thinking that the second assessment's probably going to be a quiz style assessment. So I'll check back in with you guys next week about how the quiz portion went and if you liked it or disliked it or what things you'd like to see changed. And then, yeah, we'll roll with what the majority of folks are feeling. Okay, I'm gonna shut up for 2 seconds and let you guys either like give me a thumbs up or a yes in the chat if you're happy. If you're unhappy, that sucks. And let me know if there's anything I can do to make you more happy. Cool. So a few folks are thinking they're pretty happy. If you do have questions, you know how I'm pretty good at getting back to email. So get those emails out this week if you do have some questions about that. And I will be happy to answer those questions before the weekend. So yes, lesson plan is due on the Sunday at midnight. Yep, so February 7th at midnight. And the quiz is due on the Saturday, by Saturday at midnight. Yes, that is correct. I wanted to give you guys a little bit of space in between both, just in case. But that quiz should be open, so you can do that quiz anytime this week. You don't have to wait until February 6th if you do not want to. Same with the lesson plan. If you want to get that going and get that done early, the Dropbox should be open for you, so you can submit those whenever you're ready. Okay, I would like to do a little bit of a review before moving into our lesson on place value, into our second chapter. So I just want to review what did we do on the weekend? We did Cartesian product, we did cardinality as well. So I just want to review some of these topics and maybe connect them a little bit to Venn diagrams. Okay, so let's just do a little recap here. So we're going to use what we call a universal set. So this is capital U. And let's take, I don't know, the first few letters. So let's take A, B, C, D, E, and F. Okay, so we're only going to consider the first 6 letters. Let's put a few letters inside of set A. So let's give set A little a, just for funsies, and we'll give it B as well. And let's give set B, let's give it itself, because that's fun. And then we'll put a couple other things in here. Let's put BC. BC. Any religious people out there? We're going to set B is going to be very religious this morning. BCE. Okay, and let's do some stuff. So one, let's draw a Venn diagram of what this looks like. So let's start there. All right, so we have just 2 sets, A and B. Okay, so A and B should look something like this. And I'm drawing them with an overlapping region because looking at these sets up above, it does look like they're going to have a shared element. So which element is inside of the intersection of A and B? Can you guys see that? Yeah, so our lowercase b, yeah, is going to go inside the intersection of A and B like this because it's a shared element. And then we have to go back to our sets and kind of figure out what we have left over, right? So inside of A, we have A left over. And then inside of B, we have C and E left over. Okay, so here's what A and B look like. Then we also have this universal set. So remember the universal set, if we have stuff inside of the universal set, but not necessarily inside of the 2 sets that we're working with, we just kind of put them outside. So we have A, B, C, so D I think is missing, right? So D would be on the outside, E and F, right? So that should take care of our 6 letters. So D and F just happen to be on the outside of sets A and B. And if you want, we could put some kind of boundary around these sets if we wanted to, and we could call this boundary U. So it's up to you. If you want to do that, you can. It's not necessary, but this is a nice Venn diagram of our particular sets. So 2. So let's calculate some cardinality, right? So here we're going to use these absolute value bars to denote the cardinality. And it depends on the textbook that you're looking at or the internet sources. Sometimes you'll see it written with an N as well. So hopefully I let you guys know that. It's been a while since I've looked at those couple of videos that I posted for you. I think I recorded those last year, but I think I probably gave the alternate version of cardinality in there as well. So either we use the absolute value bars, or we can use like N with the brackets and put our set that we're working with inside the brackets. So either way, this is essentially asking us to figure out how many elements are inside of these sets. All right, so how many elements are inside of A? Yeah, it's totally not a trick question. I agree with you, Ryan. There's 2. And that's because, yeah, we can come up here, we can kind of look at set A. Set A is what I've highlighted here. There are 2 elements inside of set A, or we can go back to the statement of what set A looks like as a list. There's 2 things inside of A, so the cardinality of A should be 2. Either way we go. And then 5 should be, I think 5 would work. No, 4 would work. Yeah, exactly. So we have to be a little bit careful because they have a shared element. So if I look at A and B, they share an element. And because they have a shared element, I don't want to count that twice. So yes, I think 4 is going to be the answer we want here. Or we can come down to the Venn diagram and remember that A union B is all of the elements inside what I've circled here. This is A union B, and there's 1, 2, 3, 4 elements inside of here. Yeah. Okay, so what we could do if you wanted to, you could also write out as a list, A union B contains the following elements. So we know the cardinality of A union B must be equal to 4. We essentially don't want to double count the lowercase b. All right, so let's do some more computations involving A and B. So we're going to try to calculate the set, the B complement set, so the not B, and then we're going to try to calculate a Cartesian product with B, just so that we have another example of that in our notes. And so just to kind of remind us, refresh our memory here, I'm just going to rewrite down B. So B is B, C, and E. Okay, so let's think about what not B is. So a couple of different ways we can do this. If I shrink this down, we can kind of look at the universal set. So we can look at our 6 letters, A, B, C, D, E, and F. And then, as Alyssa said, we can kind of check off the ones that are not inside of B. So A, D, and F should fit the bill here for the ones we're looking for. So A, D, and F should be what we want. And if we highlight not B, it's going to be everything outside of this circle. So if this circle is B, all of the letters that fall outside of this circle are not B, or the complement of B. Okay, so A, D, and F, I can kind of see that visually are the letters that are outside of this circle. Nice. Okay, here comes the fun part. Cartesian products are always a little bit of a pain in the butt to write down, but we'll do this just because we can. And what do we have? A and B, I think, right? And we have B already. Okay, the Cartesian product is a little bit of a pain in the butt, but it goes something like this. It's the set of ordered pairs of A and B. So essentially, we kind of walk up to, I always think of it in a restaurant kind of way. I walk up to the restaurant. On the menu, I have like 2 choices under column A. So I have little a and little b. And I have 3 choices underneath column B, little c, and little e. And my goal is to figure out how many different ways I can order these things and what that looks like. So I'll start off with, let's say, the first couple, and then you guys can maybe start filling in or seeing the pattern here. So we choose something from set A first. So I'm going to choose the little a, and then we have to choose something from set B. Okay, so A, B would be the first element or the first pair inside of the Cartesian product. Okay, so right now we're working with this one and this one. Okay, so that's one possible pairing I could make. Now I'm going to stick with A from set capital A, and I'm going to move over and choose the next element from set B. Okay, so I'm going to move over and I'm going to take little c. Okay, and then once again, I'm going to move over and I'm going to take the next element of B. So I'm trying to kind of write these down in I would say like a clever way, right? I'm trying to make sure that the way that I'm processing this gets all of the possible pairs. So I stick with little a from set capital A, and I scroll through the 3 elements from set B. Once I've done that, then I know that I have essentially paired all of the things from B with this little a, and then I move over to this little b. And then I do the same thing. I have to pair little b with all 3 elements from set B. Okay, so then we have B, BB. I got BC. And then we have B and E. So those would be all the elements in the Cartesian product of A and B. So all the possible ways we could make our choice from the menu, essentially. Does this make sense? How many elements should we have inside of the Cartesian product? So in other words, does the cardinality make sense based on the information we have? I think so, because all we really have to do to figure out how many elements, how many pairs should be in the Cartesian product is to multiply together the cardinalities of capital A and capital B. Okay, so capital A has 2 items inside of it. Capital B has 3. So I know that the cardinality of the Cartesian product has to be 6. And that's a good thing. We do have 6 elements. Okay, so it's just a little, you can kind of do that mentally as a little verification check if you'd like. So there you go, a little bit more work, just kind of reviewing some of those basic operations. Hopefully that's, is there anything else that you guys want to see before we move into our next big chapter? Could we do the multiplication? Yes, you could totally do the multiplication before writing them all out. And it also depends on the statement of the question too, right? So just be mindful of that. If it wants you to find this, then it wants you to write out all the elements. But if it wants you to find just this, then you don't need to write out all the elements unless you want to. Or sorry, write out all the pairs unless you want to. In this case, you could just jump to that number answer, right? Just tell me how many things are inside of that set. So yeah, even before starting, right? Like if capital A and capital B had more stuff inside of it, and I wanted to make sure that I found all of the stuff, yeah, maybe it makes more sense to do that multiplication first, figure out how many pairs I should have, and then start writing down all the pairs I can find. In our case, capital A and capital B were smaller. So I was like, well, it's not too hard to find all of the pairs here. I have a pretty good systematic method, and I'm using the cardinality just to double check. It's not a 100% guarantee that you'll have all the pairs because maybe you accidentally wrote down the same one twice, but at least we know how many we should have. We should have 6. Yes, that is correct, Vincent. So yeah, so Vincent brings up an interesting thing here. So this is the first kind of operation where A and B having a shared element, it actually gets counted twice, right? So Vincent's kind of talking about this shared element of small b, and it turns out that we get an ordered pair that is small b, small b. So yes, so shared elements, this is the only operation really where we want to um, be a bit mindful of double count. And we do need to use it twice here to get this element, little b, little b. I think that answers your question, right? All of the other stuff we've seen, we kind of only write it down once, right? Cool, cool. Yeah, good follow-up questions, guys. Okay, who's ready to talk numbers? Like, I'm kind of ready to work with numbers. I'm a math guy after all. Okay, we're going to talk about place value systems as our first lesson from chapter number 2. And then really chapter number 2 is focused on the big 4 and maybe big 5 if you want to include exponentiation. But the idea for chapter 2 is to get us more used to the whole number system, the natural number system. We're going to look at place value, how we think about place value, how we can model place value, and then work through our big operations. So we're going to learn, how to add things again and how to subtract things and multiply and divide in case you've forgotten how to do any of those things using an algorithm. And I'll show you how to model these kinds of things as well. And modeling is kind of the big thing here. We're going to work with different place value systems because there are other types of place value systems than the one that we work with. And then I'm going to break you down a little bit, make you cry once or twice, and then build you back up. So you understand how your kindergartners and grade 1s feel when you're like, no, that's the hundreds. and you're like, how do you not get this? But they won't because it's not a very natural thing. So yeah, so what we're going to do is start with just refreshing our memory on place value. And let's see, I don't. Dun, 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 dun. Okay, so let's talk about our number system. Before creation comes destruction. Yeah, pretty much. That's how math works in elementary school, I think, right? That's the just put that beside the mathematics board you have on your on your chalkboard. Okay, lots of stuff in here we should chat about. We have the name of our number system. It's often called the base 10 system or the Hindu Arabic system to give a little nod as to where these symbols came from. So they came from the Middle Eastern region. And Fibonacci is actually the one that's typically credited for making our number system famous. And I'm trying to remember his real name, Leonardo from Pisa? He was from Pisa. Let's do a little quick Google search of Fibonacci. I believe that's his name. And I do this because sometimes it's fun to research these kinds of things with your students, right? To let them know that number systems, just didn't come from nowhere. Like our number system has such a crazy, crazy background. So not Fibonacci numbers or sequences. How about Fibonacci, the person? Come on, Wikipedia, help me out here. Yes, I use Wikipedia, don't judge me. Okay, so Fibonacci, known as Leonardo Bonacci, or Leonardo of Pisa, yeah. So Bonacci, right? If I'm being truly Italian, the CC is a CH. So Leonardo Bonacci just means son of Bonacci, I think, right? If I remember correctly. Like they didn't really have last names, so their last name was like information about who this person was. So this would be like Leonardo, like Bonacci. It just means that like he was the son of something. We also called him Leonardo of Pisa, so he was born in Pisa region, but he was known. This is it. Fibonacci, I believe, is a son of Bonacci. Yes. So Fibonacci is son of Bonacci, and Leonardo was his first name. And he came from Pisa. So his father was essentially a trader. And if I can open up a little Google map for us, I can show you kind of the region that they were kind of trading in and around. Did I go to, I went to Gmail. How about Google Maps? I don't really need you guys to see my Gmail. It's not that exciting. It's basically just bills. Okay, and if we zoom out from Penticton and head over to the European region, we can pretend that we can go there and that we don't have to pay $2,000 to re-enter Canada. Okay, so here is Italy, if you have never seen or been to Italy before. And Bonacci, who was Fibonacci's dad, kind of traded, I would say, in and around the Mediterranean area. So he did a lot of kind of trading in and around Italy and around, so he would have been like heavily into Greece and like some of the Middle Eastern countries here, in Egypt, of course, like all of these places were very big places of trade. Of course, you can see kind of where Rome is. At the time of Fibonacci, the Romans, I believe, were still in power. So the main number system they were using was the awful Roman numerals that maybe you guys have heard of before. And Roman numerals were just not great for doing computations. So being traders and actually having to add and subtract monetary values, it was not easy to do that with Roman numerals. So when Fibonacci visited some of these Middle Eastern regions, and be mindful too that if you don't know a little bit of the history of Northern Africa, a lot of these places here in Northern Africa were taken over by the Muslims at the time. So Muhammad's followers. So all of these were very much connected to each other. And they were all using this brand new number system that we're going to talk about in a moment. So as Fibonacci did his travels with his father, he saw this new number system and started to write about this new number system in his book. So that's kind of the history of how it came to the Western world. So these symbols were used quite a bit in the Eastern world, but yeah, it was kind of this clash of Roman numerals being awful for computations and Fibonacci being like, whoa, like look at this brand new number system, it kind of makes sense. And so he tries to influence the Western culture to use the number system. And it's what we call a base 10 system. Okay, so it uses, I don't want to say the numbers, it uses the symbols. So we start with the symbol 0, which is a very special kind of symbol. And of course, we go up to the symbol 9. Okay, so these are our 10 symbols that we're allowed to use. And essentially each place value is allowed to hold one of these symbols, okay? And we often call it a positional system as well. So if you see that terminology pop up, that's because it's kind of this really nice idea of having a placeholder. So each position means something, and we'll talk about what that phrase means. But there are some systems that are not positional systems that we know about. So so for example, a non-positional system would be the old Egyptian counting system. And the old Egyptian system also had symbols to represent quantities or represent cardinality, but they could just write them down in whatever order they want. Um, and I'll give you an example. So they had, well, actually, I'm just gonna have to double check something in the background here, but you guys can kind of copy that down and I will just double check. So Egyptian number system. Actually, I will flash it on, I have a little picture here that I can show you guys. So this is the Egyptian number system over here. So basically, their symbols did represent numbers like powers of 10. And they had the following symbols. So they had just like a little stick for the number 1. They had the heel of a shoe to represent the number 10. They had a coiled rope to represent the number 100. A lotus flower to represent the number 1,000, a bent finger to represent 10,000, a tadpole to represent 100,000, and my favorite is the astonished man to represent 1 million, because you could never, like, who would ever have 1 million things? You would just be astonished, right? Back in the Egyptian day. So these were the different kinds of symbols that they would use to represent things. And I'll show you an example of how they might write down a couple different numbers. So if I wanted to write down, for example, the number 100, in Egyptian, we would just write down a single coiled rope. But if I wanted to write out, say, the number 200, we didn't really have a symbol to represent the number 200, but we had a coiled rope to represent 100. So what they would do is they would just write out 2 coiled ropes. Now, we know the number 10, for example, is a heel, so the back of a shoe, essentially, like the mark you would make walking through the desert. And of course, if I wanted to write out something like 210, I would just combine all of these things together. So I do like 2 coiled ropes and then a heel bone. But it didn't really matter the order that I put stuff in. So I could have written it like this. So this is what we mean by non-positional. The largest symbols don't necessarily have to come first. And in fact, if you go look at some of the old Egyptian artifacts, sometimes the numbers were kind of all over the place. And so that's a little indication of what the Egyptian system looked like. It would be a non-positional system because the order that these numbers came in doesn't really matter. And then the Egyptians also didn't have a symbol for the number 0. They couldn't talk about the empty set either. So not having a number to represent emptiness, and they honestly, they didn't really need it because they had a non-positional system, and you would just kind of add up all of the symbols and kind of make sense by looking at the symbols that were there. Talking about nothing didn't really make any sense to them. And of course, talking about negative quantities also just didn't really make any sense to them. So they didn't really have symbols to talk about that kind of stuff. You would never walk up to somebody, how many, can you give me 0 things? It didn't make any sense to them, right? So that's my assumption as to why they didn't necessarily have a symbol for 0, because they didn't really have to use that in practice. Now, to my knowledge, Roman numerals also didn't have a place value for 0, which was kind of one of the shortcomings of that system. Another common system you might see as you're kind of doing a little bit like looking around in place value systems is the ancient Babylonian system. And they were wild. The Babylonians were kind of crazy. They were like, you know what is really going to work for us? We're going to use a base 60 system rather than a base 10 system. So each of their place values essentially could contain one of 60 symbols instead of one of 10 symbols. And I'll give you a couple examples here as well. So the Babylonians would have been in that kind of Middle Eastern region, so they used a lot of clay to do their number writing, and they had reeds. They had these kind of hardened reeds that they would use to essentially imprint letters and symbols onto this wettened clay. So often you'll hear the word cuneiform being used. And cuneiform is essentially this action of using the reed to make imprints onto the tablets that they were working with, the kind of wet clay. And they had kind of 2 main symbols, and I'm trying to remember. So they have this symbol, which I believe, so they could use the side of the reed to make an imprint, and it kind of came out looking like this, and I believe that was 10. And I think the other one was a triangle with a stick on it. So if I have it here, yes, here are some examples. And so, yes, so they could go one way or the other. So they had the ability to kind of imprint by pressing down, or they could kind of swap it over to the side and do an imprint. So they had essentially a I always draw it as like an upside down triangle with like a little stick on it. Okay, this was the number 1. And then they had this kind of sideways triangle made from it and just kind of rotating the reed around and imprinting. And I believe that was 10. Yes, that was 10. Now, because they did have a positional system, each of their place values actually had meaning. So each of their little place value boxes, we could start with the units, but then it would go up by some power of 60. And we'll see how this kind of connects to our positional system. Ours goes up by powers of 10, essentially, instead of 60. So for some reason, they thought 60 was like the be all end all, probably because of astronomy. So 60 times 60 is what, 3,600? So they probably thought that that was a nice number to do work in like astronomy with. So a lot of these older systems used weird bases because it was easier to work with like the year. Like we have 365 days, but for them 360 was good enough. So they usually tried to create a base system that worked with 360 is typically what the historians think. So let's say we wanted to, I don't know, write out the number 10. Okay, so of course, if I wanted to write out the number 10, I would just put 10 in the units column, and we were kind of done. We didn't have to put a symbol inside of the 60s column. Now, what if I wanted to write out the number 60? Now, this would be very similar to how we write out the number 10. What they would do is they would put a single stick inside of the 60s column, and that single tick would represent 160, kind of like how we write out the number 10, right? It's similar to how we put the symbol 1 in the tens place value. That represents a 10, and then we put nothing inside of the ones place value. So a similar kind of situation here. But notice, because they don't have the number, they don't have a symbol for 0, this is how we would write it. It would be written out like this. But how do I write out the number 1? Well, I could write out the number 1 like this. So as we're going to read Babylonian tablets, the number 1 and the number 60 are actually written out in the same way. It's hard to distinguish whether or not these people are talking about the number 60 or whether or not they're talking about the number 1. And you kind of have to figure out what number they're using based on the context of what's written on the tablet. And if you can't read ancient Babylonian, that's quite hard. So this is the problem with this. I mean, the positional system is a good idea, but this is the downfall of not having a symbol to represent an empty thing, right? A place that's empty. This is why 0 is such an important idea, because it allows us to make this distinction between 10 and 1, or in the Babylonians' case, between the number 60 and the number 1, which actually looked the same. Now, when I say tablet here, I don't mean like what you're using to make your notes right now. I mean like legitimately a clay tablet. Okay, this is often why we call a 0 a placeholder kind of symbol, because it allows us to make that distinction between, in this case, 60 and 1, or something like 100 or 10 or 1. So it ensures that those numbers that we write down actually look a little bit different, so we understand what the cardinality is of those particular numbers that we're working with. And one last really nice system was the so if you're kind of a history person and want to look into this, another fun system is the ancient Mayan system. Now, for the most part, their system was a base 20 kind of system, so it relied mostly on powers of 20. It was a little quirky, though, in the first couple of place values. They actually used 18 as one of their first place values, and I think that's because 20 times 18 gets us pretty close to that 360 again, if I remember correctly. That would be 16, 10, and 2, so that gets us to 7. 378. Maybe I'm wrong here. Anyway, If you do go do, I'm not going to write out any numbers because I don't want to lie to you and make a mistake, but they essentially had 3 different symbols. They had a pebble, they had a stick, and then they had an empty shell. Or as I like to say, Minecraft bread. So you have a pebble, which represented the number 1. This is a pebble. You had a stick, which represented the number 5. Then you had Minecraft bread, or a shell, to represent their place value. So this was their number 0. It was essentially a shell. And notice that these are all very common objects that you could find in nature in South America, especially living on Chile around the coast, which is, I believe, where the Mayan people were from. And so, yeah, so they could easily collect these items, talk about small numbers with these items. If they needed to, they could draw these symbols very easily on the sand or in the dirt as well, if they needed to show these symbols to other people that knew the number system. So yeah, those are a couple earlier number systems that are very common to discuss usually in college, but I think they're fun. They're fun kind of ways to connect history to mathematics, especially when learning about place value as well. So let's talk about our place value system. And essentially, a place value system is going to require a couple things from us. The first thing that a place value system needs is a set of symbols to allow the reader to know the quantity of the thing that we're talking about. Now, these symbols vary from culture to culture, especially our ancient cultures. So for example, the base 20 system that the Maya would have used had 3 symbols. It had a symbol for the number 1, a symbol for the number 5, and a symbol for the emptiness, so a shell here symbol. So 3 symbols in their particular system, and that worked for them. For us, we require 10 symbols, the numbers essentially from 0 to 9. But a set of symbols is not the only thing that we need. We need a structure or a way to let the reader know the cardinality of what we're talking about. So there also has to be some kind of rule about how to use these symbols to make the number. Okay, and I'm going to use the word cardinality here to talk about, like if I have, usually back in the day, we'd be like hunter-gatherers. So, I have 5 apples or something, right? And so I need to somehow connect the symbol to this quantity of 5, right? So I'm thinking about cardinality here specifically when thinking about these place value systems. So for us, so for a base 10 system like ours, of course, number 1 is satisfied with the following 10 symbols. Wow, that's great. Great penmanship, Brian. Well done. And our set of rules are each place value represents some kind of power of 10. Okay, we haven't really talked about exponents yet, and we will talk about that closer to the end of this chapter. But I'm hoping that you know what I mean by a power of 10. So if we look at our place value system, we might have something like the following. So I'm going to write out a decimal number here that has a couple. Let's go up to here, and I'm just going to move this over a little bit. So I do want to get up to, let's say, the millions, just so that we have all of our terminology correct here. So we do have our decimal place here. And let's write out a large number. So let's do like 1,345,201 point, I don't know, 978. So this is a big number. It represents the number of dollars I wish I had in my bank account. And each one of these boxes, these black containers that I have, represents a specific place value. Okay, so each one of these boxes is a place value. And each one of these place values does have a name. So starting with the units or the ones. So let's see if I can, how do I do this in a nice way? So we have like the ones or the units. You guys can kind of turn your paper sideways to do this. I'm gonna have to just try to like tilt my head and make this work. So we have the ones or the units as essentially our first place value. That's the very first kind of place value positioning we learn. And then we start getting eventually up to the tens, right? So like 10, 11, 12, 13, 14, all that requires the tens place value column. And then we start working our way eventually up into the hundreds. Okay, so those are our first three place values that we essentially learn about. And then, as we start to go a little bit further in our elementary school career, we start learning about the other kinds of place values too. So we have like this collection up here. This is called like the thousands. And we have the thousands, 10,000s, and 100,000s. And then we eventually get up into the millions. So we kind of chunk ours up into groups of three, right? So the first one you can call like maybe the hundreds chunk, right? So this chunk of three, sometimes we call this the hundreds chunk, because every number in here represents some kind of hundred. Then we move over into the thousands chunk of three, and then we move into the millions chunk of three. So we always are grouping in groups of three. And of course, it's always 1 that thing, 10 that thing, 100 that thing. So 1,000s, then 10,000s, then 100,000s, 1 millions, then 10 millions, then 100 millions. So it's always chunked in kind of this really nice patterned way. Okay. And then when we eventually start learning about decimal places, we have movement in the other direction as well. Do you guys remember what your decimal places are called? So what's this first decimal place? Do you remember the name of this first decimal place? It starts with a T. Well, I mean, a negative does come into play, so hold on to that thought for a moment. But this decimal place over here, this is called the tenths column. So this is this column essentially represents X number of tenths of a whole unit. So if we think about this column in terms of dollars and cents, this would represent like the dimes, right? And a dime is 1/10 of a loonie, a dollar. So we call this the tenths column. because it takes 10 of these in order to get back to a whole, essentially, a whole dollar, right? It takes 10 dimes to get to a dollar. The next one over, so the 7 is in what column, do you think? How many of these things do we need to get to a dollar? Yeah, we need 100 of these things to get to a dollar. 100 pennies in Canadian money would get us to a dollar, so we call this the hundredths column. Okay, and then I'm just going to go one more place because it's very common to go up to 3 decimal places. This would be the thousandths column. Okay, and notice that they're very similar to the wording that we have over on the left-hand side. The only difference is they end in THS instead of ending in a D. That's the only real difference between the place values we have on the right-hand side. So that's the word that goes along with this particular number. Let's actually look at one more thing before we kind of move on from this topic. So Alyssa had mentioned something about negative, and I told her just to hold on to that for a hot second. And so that's what I want to do here. Let's just see how we can connect this to powers of 10. Okay, so here's our number once again, 1,345,201 decimal 978, or 978 thousandths is how we could say that too. Now, each one of these specific decimal places actually represents what we call a power of 10. So I'm going to write out those powers of 10, and then you can either agree or disagree with me, and we can fight to the death if you would like. I would prefer not to, but I'm trying to space these out a little bit so that I can actually draw like little boxes underneath them, and I'm failing miserably. That looks a little bit better. And then I might want to space these out a touch too. So 9, 7, and 8. Okay, so here is our number once again with all of the place value boxes, just to kind of help illustrate where things are. And in red, I'm just going to go along underneath all of these, and I'm going to write out the power of 10 that corresponds to the place value we're working with. So we'll start with 10. All right, so obviously, if I'm in the tens place value, that must be 10 to the power of 1. It must just be itself. Now, 100, or the hundreds column, is going to represent 10 to the power of 2, because 10 times 10 is equal to 100. And what you're going to notice as a pattern as I keep moving towards the left is we're going to get higher and higher powers of 10. So 1,000 is 10 times 10 times 10. This particular place value is the thousandths place value, which is the 10 cubed place value. And this is important because it is going to tie into some of the manipulatives that we use here today. Okay, so all the way up to the 1 millionths place value, which would represent 10 times 10 times 10 times 10 times 10 times 10. So multiplying 10 by itself 6 times. Now, for the ones place value, or the units, one thing we're going to discuss a little bit later in our course is that anything raised to the power of 0 is always 1, as long as the base isn't 0. So if I want to figure out kind of how to extend this pattern towards the right side of this decimal place, I just have a look at the following pattern. So as I'm moving this way along my place value, I'm decreasing by 1 every single time. So if the tens column is 10 to the 1, kind of makes sense for the next column to be 10 to the power of 0. And then this pattern keeps going over on the right-hand side. So our first decimal place is 1/10. And we'll take a look at, this number here. 10 to the negative 1 is really like saying 1/10. Or 1/10. So that's how we label this particular column as a power of 10. This is the tenths column, so it gets 10 to the negative 1. And then the big pattern on the right-hand side is that our powers of 10 keep decreasing by 1 as I move towards the right. So 10 to the power of -2 is really 1 over 10 squared, so 100th. And 10 to the -3, we'll see a little bit later, is 1 over 1,000. So this is the thousandths place value. So this is what we mean when we say powers of 10. And this is pretty powerful. So the idea of powers of 10 is really nice because it allows us to write numbers in an expanded kind of way. So I'm not going to take the same number here because I think that's kind of annoying, but let's take a smaller number like 3,261. Now I could take this number, 3,261, and I could rewrite it if I wanted to in what we call expanded form. And so I'm going to write out two versions of expanded form. Okay, so this is what we call expanded form. And the idea here is to make the connection between the place value and the actual symbols that we're using. So if I look at the number 3,261, we can think about that number as 3 times 1,000, or the symbol 3 is in the thousands place. The symbol 2 is in the hundreds place. The symbol 6 is in the tens place, and the symbol 1 is our unit, or our ones. So that's the idea of expanded form, is it really shows which symbol lies inside of which particular place value. And the main manipulatives that we use at the elementary school level. And when I say manipulative, I mean some kind of concrete thing that allows us to teach mathematics. So I had a couple, sorry, had to lean back there pretty far. I have a couple manipulatives here. I actually don't have any base 10 blocks, unfortunately, to show you on screen, but here are a couple kinds of common types of manipulatives. So as we're teaching fractions and things like this, we might have fraction strips. These are magnetic so that I can kind of tack them onto boards and stuff. So this would be a kind of manipulative because we use this to help visualize fractions and problems with fractions. Other manipulatives that we're going to discuss and kind of briefly think about in this course are the algebraic kind of manipulatives as well. So we have, we call algebra tiles. So we have symbols that represent x and symbols that represent the square of x, right? So x times x. And we can use these manipulatives to kind of think about algebraic problems involving x's and x squareds. So this is what I mean by a manipulative. So something that you can use as a teacher to kind of help connect a concept together. So we call these like concrete items. And for us, base 10 blocks are the main manipulative that I just want to introduce you to. So if you want to do a little bit of research, you can go take a look at base 10 blocks online. You can probably find some really nice like PNG or JPEG images for base 10 blocks. It's probably good to just save those as separate images. And that way, if you need to make a BLM using base 10 blocks, you already have those pictures ready to go for you. That's usually what I have in my base 10 blocks JPEGs just kind of stashed in a subfolder somewhere. I don't know where they are. But we have kind of our main base 10 blocks. We have usually just a giant block like this. We have a, we call it a flat, so kind of a thinner bit of that cube. We have the rod, which is kind of one little bit, so kind of like a tall square prism, essentially. I'm a little shaky today after 2 cups of coffee, so bear with me here. I'll flash some pictures of these so you can see them after. That's not a very good, this is supposed to be a 3-dimensional like square prism shape. So do your best. It should look kind of like a McDonald's French fry is what I'm trying to go for here. So these are our four basic manipulatives, and we're not going to have to draw them out in 3 dimensions all the time. But I'll just introduce you to what these are. And we'll take a look at some pictures, and that's probably good for today. So down here at the bottom, this is our ones unit. This represents the number 1, and it's just a little tiny cube. If I put 10 of these cubes together, we get the rod. So sometimes you'll hear this called the rod, which is overtly sexual for something that you would ever discuss in elementary school. But anyway, this is sometimes called a rod, and this is 10 ones put together. So this is our tens unit and represents a single 10. Moving up, we have the flat. So once you're old enough, you get to move out of mom and dad's house into the flat. And a flat is essentially 10 tens put together to get 100. So this is our visualization of the number 100. And then we have the cube. Okay, so the gigantic cube is 10 flats put together to get a thousands cube. And I mean, what's really nice too here is that you have this nice connection to a visual. So 1,000 is what we say 10 cubed, right? Is 10 cubed. So it's no coincidence that the thing that we have over here is a cube, because 1,000, we think about that as a 10 cubed. And kind of same thing here. If I want to read this out loud, we might say 10 squared is 100. And notice that what I have over here, when we go to look at these online, this is a square. So this is how we think about a 10 square. And we think about it as a this kind of really nice shape, right? So it's no coincidence that these manipulatives are kind of tied to this kind of terminology. So as you finish copying that down, if you have any questions, feel free to jot them into the chat, but I'm just going to look up base 10 blocks on Google so you guys can kind of take a look at what these things might look like, okay? Okay, so I'm just going to bounce over here so you can kind of take a little peek. And then that's really it for today. So you can see the cube, the flat, the rod, and the unit. So these would be very common things, especially if you're teaching in the younger grade levels. You definitely want to grab several sets of these through your school. Hopefully your school will have a bunch of these to use too. Yeah, so that's kind of what they look like. Notice the cube has a bunch of these little units inside. The cube would technically have 1,000 units inside. The flat would technically have 100 units inside of it, and the rod would have 10 units inside of it. So yeah, we will take a look at how to utilize these manipulatives to do some addition kinds of things on Wednesday. Okay, so I'll bounce back over to our notes just in case you have to copy something down. But if you got places to go, people to see, get out of here. Have a great day. And I will see all of you on, yeah, I'll see all of you on Wednesday for sure. You are very welcome, Chloe. Thanks for tuning in. And yeah, no worries, guys, no worries. Khan, I got your email. I will send you an email later today after my calculus class, okay? Why are there weird noises? Like, where is this coming from? Why has this started today? I don't get it. Okay, anyway, I'm going to sign off, guys. Not seeing any questions in the chat. So have a lovely, lovely day, and I'll see you guys soon.